Imagine standing at the edge of a primeval forest, your feet sinking into soil that holds secrets dating back nearly 13,000 years. The trees around you whisper tales of a time when the world plunged into sudden, devastating cold, reshaping landscapes and perhaps altering the very course of human civilization. Picture this: an Earth recovering from the last ice age, warming gradually, life flourishing. Then, without warning, temperatures plummet. Glaciers advance once more. Entire ecosystems collapse. And in North America, an entire culture of prehistoric humans, the Clovis people, seemingly vanish from the archaeological record. This catastrophic cold snap, known as the Younger Dryas, represents one of the most abrupt and severe climate shifts in Earth's recent history. The conventional explanation, that melting ice sheets disrupted ocean currents, seemed sufficient for decades. But what if something more dramatic triggered this global cataclysm? What if, as some researchers now propose, the Earth encountered something from beyond, a comet or asteroid impact so devastating it altered our planet's climate trajectory? The controversial Younger Dryas Impact Hypothesis suggests exactly this scenario, challenging decades of accepted science. Tonight, we explore the evidence for and against this revolutionary hypothesis. We'll examine microscopic diamonds scattered across continents, strange metallic spherules embedded in ancient soils, and geological formations that defy conventional explanation, all potential fingerprints of cosmic catastrophe. We'll hear from scientists on both sides of this contentious debate, those who see compelling evidence for a cosmic impact, and those who dismiss such claims as methodologically flawed or simply misinterpreted data. The stakes couldn't be higher for our understanding of Earth's past, because hidden within this scientific controversy lies something profoundly important: insights into how vulnerable our planet truly is to sudden, devastating change. The Younger Dryas wasn't just a climate event, it was possibly a turning point that redirected human history. If the impact hypothesis proves correct, we must reimagine not just climate science, but potentially the origins of agriculture, early religion, and the rise of complex societies. The rapid cooling may have been the catalyst that drove humans to abandon hunting and gathering in favor of farming. For the skeptics, the impact hypothesis represents dangerous pseudoscience, a distraction from sound research and established understanding of Earth's climate systems. They point to methodological flaws, contaminated samples, and the allure of catastrophism over more mundane explanations. Tonight, we examine what the evidence truly shows. We'll separate speculation from fact, explore the latest research, and dive deep into one of the most fascinating scientific controversies of our time. This is not merely academic debate. It's a mystery about our planet's vulnerability to cosmic forces. The truth, as we'll discover, is nuanced and complex. Neither side possesses all the answers, and the debate itself reveals much about how science grapples with uncertainty and competing evidence. We'll walk the line between genuine scientific inquiry and the human tendency towards sensational explanation. Because beneath this controversy lies something universal: our need to understand catastrophe. Whether ancient humans witnessed a cosmic impact or simply endured a climate shift triggered by natural Earth processes, they faced devastation on a scale we can scarcely imagine. Their story may hold lessons for our own precarious moment on Earth. As we face contemporary climate change, understanding past catastrophes becomes not just academically interesting, but potentially crucial for our survival. History, even prehistoric history, has much to teach us. So tonight, we journey back 12,800 years to a world poised between ice and warmth, between hunter-gatherer existence and the first stirrings of agriculture. We'll examine evidence ranging from lake sediments in Europe to cave paintings in Turkey, from ice cores in Greenland to ancient soils across North America. We will uncover what happened during this mysterious period and why the clues have proven so difficult for scientists to interpret definitively. We'll see how new evidence continues to emerge, sometimes supporting and sometimes challenging the impact hypothesis. We'll explore why some researchers remain steadfastly opposed to the impact theory while others find it increasingly compelling. And we'll consider what these competing viewpoints reveal about science itself, how it progresses, sometimes haltingly, toward deeper understanding. Our journey begins with strange black mats found buried beneath North American soil, carbon-rich layers dating precisely to the onset of the Younger Dryas. Within these dark boundaries lie microscopic clues that some interpret as cosmic calling cards: nanodiamonds, carbon spherules, and platinum anomalies. Yet others see nothing extraordinary in these layers, just the expected residue of natural Earth processes, perhaps wildfires or normal geological activity, misinterpreted by researchers too eager to find evidence supporting a dramatic cosmic impact. Tonight, we examine the evidence with fresh eyes. We'll consider what conventional science gets right, what the impact proponents bring to our understanding, and what mysteries remain unsolved regardless of which theory ultimately prevails. The truth, as always, resides in the evidence itself. And as we sift through this evidence together, we'll discover that the Younger Dryas represents more than an ancient climate event. It offers a window into how Earth's systems respond to sudden perturbations, whether triggered from within or beyond our planet. Chapter 2. The Stakes of Ancient Climate Catastrophe. The Younger Dryas wasn't merely a climate event. It was potentially a civilization-altering moment that reshaped human destiny. To grasp its significance, we must first understand its scale. Global temperatures plunged by as much as 15 degrees Celsius in some regions, and this happened not over centuries, but decades. Imagine generations of humans who had adapted to warming conditions suddenly facing winters of unprecedented ferocity. Game animals migrated or vanished. Plant foods withered. The relative abundance that characterized the post-Ice Age world abruptly disappeared, replaced by scarcity and hardship across continents. This climatic reversal happened precisely when human societies stood at a crucial threshold. In the Near East, early experiments with plant cultivation were underway. Hunter-gatherer groups had established semi-permanent settlements. The foundations for what would become agriculture were being laid. The timing could not be more significant. Did the Younger Dryas catastrophe, whatever caused it, actually accelerate humanity's transition to farming? Did the desperate need for reliable food sources in a suddenly hostile climate push our ancestors toward agricultural innovation? If so, everything that followed, cities, writing, metallurgy, organized religion, complex social hierarchies, and eventually modern civilization itself, might trace its ultimate origins to this climate catastrophe. The stakes of understanding the Younger Dryas couldn't be higher for human history, but the implications extend beyond historical curiosity. If the Younger Dryas was triggered by a cosmic impact, as the hypothesis suggests, we face troubling questions about Earth's vulnerability. How frequent are such events? Could something similar happen again? Would we see it coming? More importantly, could our understanding of this ancient event help us prepare for future catastrophes, whether cosmic or climate-related? The Younger Dryas represents a natural experiment in rapid climate change, one that modern science is still struggling to fully comprehend. For geologists and climate scientists, the Younger Dryas presents a profound puzzle. Its onset was too rapid for conventional explanations. The prevailing theory, that freshwater from melting ice sheets disrupted Atlantic circulation, explains much but leaves questions unanswered. The disruption of ocean currents should have cooled the North Atlantic region primarily. Yet evidence shows the cooling was more widespread, affecting regions as distant as New Zealand and South America. Something more than ocean circulation seems necessary to explain the global pattern. Furthermore, the conventional explanation struggles to account for the abruptness. Climate models suggest ocean circulation changes would produce cooling over centuries. Yet ice core records indicate the Younger Dryas cooling occurred within decades, perhaps even faster in some regions. The impact hypothesis offers a compelling alternative: a cosmic collision that ejected massive amounts of dust and debris into the atmosphere, triggering rapid cooling through reduced sunlight. This mechanism could explain both the suddenness and the global extent of the climate shift. Such an event would have profound ecological consequences beyond temperature change. The impact proponents suggest widespread wildfires ignited across continents, evidenced by carbon-rich black mats found in archaeological sites. Entire ecosystems may have collapsed simultaneously. For the Clovis people of North America, sophisticated hunter-gatherers who had spread across the continent, this would have been apocalyptic. Their distinctive stone tools vanish from the archaeological record precisely at the Younger Dryas boundary, suggesting cultural collapse or dramatic adaptation. Similarly, large mammals that had survived millions of years of previous climate fluctuations, mammoths, mastodons, giant ground sloths, and numerous other species, went extinct during this period. The impact hypothesis offers a potential explanation for this remarkable coincidence. If these extinctions were triggered by impact-related wildfires, climate change, and ecosystem collapse, rather than human hunting as commonly believed, our understanding of humanity's role in prehistoric ecology might need significant revision. The stakes for paleoecology are enormous. Beyond scientific implications, the Younger Dryas controversy reveals much about how modern science handles revolutionary hypotheses. The impact theory was initially met with extraordinary skepticism, sometimes verging on hostility, from the established scientific community. This reaction reflects science's necessary conservatism. Extraordinary claims require extraordinary evidence. But it also demonstrates the sociological dimensions of scientific debate, where careers, reputations, and research funding can become entangled with particular theoretical positions. As new evidence has accumulated over the past 15 years, positions have evolved. Some former critics now acknowledge compelling aspects of the impact hypothesis, while maintaining skepticism about specific claims. The debate has become more nuanced, more evidence-based. This evolution demonstrates science at its best, self-correcting through rigorous analysis and new data. Whatever the ultimate resolution of this controversy, the process itself reveals how scientific understanding advances, sometimes haltingly, through periods of contention and reassessment. For archaeologists studying human cultural evolution, the Younger Dryas represents a critical juncture. At Göbekli Tepe in Turkey, a massive ceremonial complex predating Stonehenge by 6,000 years, we find evidence of sophisticated social organization emerging just after the Younger Dryas onset. Could this monumental construction effort, requiring coordination of hundreds of workers, represent a response to witnessed cosmic catastrophe? Some researchers suggest these elaborate stone pillars, carved with strange animal imagery, commemorate the devastating event that transformed their world. If true, this would mean humanity's first known temple emerged as a direct response to cosmic trauma, perhaps an attempt to appease the sky gods who had brought destruction. The earliest religion might be inextricably linked to astronomical awareness forged through catastrophe. Similarly, ancient myths across cultures describe floods, fires from heaven, and global calamities that ended previous worlds. Researchers like the late anthropologist Claude Lévi-Strauss noted striking similarities in these stories across unrelated cultures. Could these myths preserve memories of actual cosmic catastrophe? The Younger Dryas Impact Hypothesis offers a tantalizing possibility that our ancestors witnessed and survived a cosmic event so dramatic it embedded itself in cultural memory, passed down through generations as cautionary tales and origin myths. Our oldest stories might contain empirical truth. If so, we must reconsider the relationship between myth and history, between cultural memory and empirical evidence. The black mats, nanodiamonds, and platinum anomalies studied by geologists might find their human complement in stories preserved for millennia through oral tradition. For modern humanity facing our own climate crisis, the Younger Dryas holds another significant lesson. Earth systems can change with shocking rapidity. The comfortable assumption that climate shifts happen gradually, allowing adaptation, is contradicted by this prehistoric example. Whether triggered by cosmic impact or internal Earth processes, the Younger Dryas demonstrates that stable climate conditions can collapse within a single human lifetime. This sobering reality adds urgency to contemporary climate concerns. Tipping points, once crossed, can unleash rapid change. Chapter 3. Earth at the End of Ice. 13,000 years ago, Earth was emerging from the grip of the last great ice age. For tens of thousands of years, massive ice sheets had covered much of North America, Europe, and Asia. Sea levels stood hundreds of feet lower than today, exposing vast continental shelves as dry land. Human populations had adapted to this ice-dominated world. In Europe and Asia, sophisticated cultures created remarkable cave paintings, carved figurines, and developed specialized hunting technologies. In North America, the Clovis people spread rapidly across the continent, their distinctive stone points found from coast to coast. The world was warming gradually. Ice sheets were retreating northward, Forests advanced into formerly frozen landscapes. Animals migrated into newly habitable regions. For humans, this warming trend meant expanding territories and new resource opportunities. The future looked promising. Then something changed. Within what might have been a human lifetime, temperatures plunged. The warming trend reversed violently. Glaciers advanced once more. Forests died back, replaced by tundra. Animal migrations patterns shifted dramatically. The cold returned with stunning swiftness. This climatic reversal, the Younger Dryas, lasted approximately 1,200 years. Named after Dryas octopetala, an Arctic alpine flower whose pollen becomes abundant in European sediments from this period, it represents one of the most studied climate events in Earth's recent history. To understand what made this event so significant, we must first appreciate the climatic context. The planet had been warming since the last glacial maximum around 20,000 years ago. The massive Laurentide ice sheet covering North America had been steadily retreating. This retreating ice created enormous meltwater lakes along the ice sheet's southern margin. Lake Agassiz, larger than all the modern Great Lakes combined, contained vast amounts of freshwater held back by ice dams. The conventional explanation for the Younger Dryas involves these dams failing catastrophically. According to this theory, when the ice dams collapsed, enormous volumes of freshwater poured into the North Atlantic, disrupting the ocean circulation pattern that brings warm tropical water northward, the Atlantic meridional overturning circulation, which includes the Gulf Stream. This circulation disruption, the theory suggests, effectively switched off the North Atlantic's heat pump, causing temperatures to plummet across Europe and North America. Climate would remain in this cold state until ocean circulation patterns could re-establish themselves over a millennium later. For decades, this explanation seemed sufficient. It aligned with climate models showing how freshwater pulses could disrupt ocean circulation. It explained the regional pattern of cooling, most intense around the North Atlantic. It connected known glacial features with climatic consequences. But troubling questions remained. The cooling appeared too abrupt in some records, happening over decades rather than centuries as models predicted. Evidence from some southern hemisphere locations showed synchronous cooling, difficult to explain through North Atlantic mechanisms alone. Perhaps most problematically, geological evidence for the theorized freshwater routing remained elusive. Researchers struggled to identify conclusively which pathway the meltwater followed to reach the ocean. The timing of known meltwater pulses didn't align precisely with the Younger Dryas onset. These inconsistencies created space for alternative explanations. In 2007, a team of researchers led by nuclear chemist Richard Firestone proposed a radical alternative. The Younger Dryas was triggered not by meltwater, but by a cosmic impact, a comet or asteroid striking Earth. The team published evidence from dozens of archaeological sites across North America showing unusual materials at a layer dating precisely to 12,800 years ago, the Younger Dryas boundary. These included magnetic microspherules, nanodiamonds, elevated platinum, and carbon spherules. These materials, they argued, were consistent with what would be expected from a major cosmic impact. The hypothesis suggested a fragmented comet struck the Laurentide ice sheet, causing catastrophic melting, widespread wildfires, and atmospheric dust loading that triggered rapid cooling. The response from the scientific community was swift and largely negative. Critics pointed to methodological issues, questioned the dating of samples, suggested contamination might explain the findings, or argued that the identified materials could have terrestrial origins unrelated to impacts. Over subsequent years, the debate intensified. The original team and new collaborators published additional evidence supporting the impact hypothesis. Critics published refutations. The scientific literature became a battleground of competing claims, methodologies, and interpretations. What makes this controversy so compelling is that it cuts across multiple scientific disciplines. Geologists, chemists, physicists, archaeologists, paleontologists, and climate scientists all have stakes in the outcome. Each brings different expertise, methods, and standards of evidence. For archaeologists, the timing is especially significant. The Clovis culture, known for distinctive fluted projectile points, disappeared precisely at the Younger Dryas boundary. Their sophisticated stone tool technology, which had spread rapidly across North America, vanishes from the archaeological record. This disappearance coincides with the extinction of 35 genera of large mammals in North America: mammoths, mastodons, giant ground sloths, American camels, American horses, and numerous other species that had survived previous climate fluctuations for millions of years. The conventional explanation attributes these extinctions to human hunting, the overkill hypothesis, combined with climate change. But critics note that similar hunting technologies in other parts of the world didn't cause comparable extinction events. Something about North America seems unique. The Younger Dryas also coincides with the appearance of widespread black mats, dark, organic-rich soil layers found across North America. These carbon-rich deposits contain unusual concentrations of materials that some researchers link to cosmic impact, while others attribute to terrestrial processes. Across the Atlantic, human cultures were also transformed during this period. In the Levant region, early experiments with plant cultivation that had begun during the warming period intensified during the Younger Dryas. The first steps toward agriculture accelerated under cold, dry conditions. At Göbekli Tepe in Turkey, hunter-gatherers began constructing the world's first known monumental ceremonial complex: massive stone pillars arranged in circles, carved with sophisticated animal imagery. This extraordinary site predates Stonehenge by 6,000 years and coincides with the Younger Dryas aftermath. The timing suggests a provocative possibility that this unprecedented mobilization of labor and resources might represent a response to witnessed catastrophe. Could the elaborate carvings, which include numerous astronomical symbols, commemorate a cosmic event that transformed their world? Similar questions emerge when examining ancient myths worldwide. Plato's account of Atlantis describes a civilization destroyed in a single day and night by floods and fire from the sky. Indigenous stories across North America recount a time when stars fell and the world burned. Chapter 4. The First Clues. The journey to the Younger Dryas Impact Hypothesis began not with a dramatic discovery, but with a puzzling absence. As archaeologists excavated sites across North America in the mid-20th century, they noticed something strange. Clovis artifacts, abundant in layers dating to around 13,000 years ago, simply vanished above a certain point. This archaeological horizon coincided with a thin, black carbon-rich layer found at numerous sites. Above this dark boundary, Clovis points disappeared, replaced eventually by different tool technologies. Something had happened to this sophisticated culture that had spread across the continent. Independently, paleontologists were documenting a wave of extinctions that occurred at roughly the same time. North America lost approximately 35 genera of large mammals, a stunning 70% of species weighing over 100 pounds, within what appeared to be a relatively brief interval. Meanwhile, climate scientists analyzing Greenland ice cores had identified the Younger Dryas as one of the most abrupt climate shifts in the geological record. The cooling happened with remarkable speed, in some records appearing to occur over mere decades rather than centuries. These three phenomena, cultural disruption, mass extinction, and abrupt climate change, all converged at approximately the same time horizon. The coincidence begged for explanation. Were they connected? Could a single causal mechanism explain all three? The conventional view held that the Younger Dryas cooling disrupted ecosystems and human lifeways, while human hunting contributed to or finished off already stressed animal populations. But some researchers found this explanation insufficient to account for the suddenness and scale of change. In the early 2000s, Richard Firestone, a nuclear physicist at Lawrence Berkeley National Laboratory, and Alan West, an independent geologist, began investigating an unusual pattern of magnetic microspherules found in soils at the Younger Dryas boundary across numerous North American sites. These tiny magnetic spherules, perfectly round microscopic balls of iron, nickel, and other metals, are typically formed through high-temperature processes. They can have multiple origins, including industrial pollution, volcanic activity, lightning strikes, and cosmic impacts. What made these particular spherules interesting was their consistent presence precisely at the Younger Dryas boundary layer, their unusual composition, and their widespread distribution across geographically distant sites. The pattern suggested a continent-wide depositional event. In 2006, Firestone, West, and a multidisciplinary team, including archaeologists and geologists, found something even more intriguing: nanodiamonds. These microscopic diamonds, some in a rare hexagonal form called landsdolite, were embedded in the same boundary layer as the spherules. Landsdolite is particularly significant because it forms under extreme pressure and temperature conditions typically associated with cosmic impacts. Its presence in sediments has been used as evidence for other known impact events in Earth's history. The team also identified elevated levels of iridium and other platinum group elements in the boundary layer. These metals are relatively rare in Earth's crust, but more abundant in meteorites and comets. Their concentration at boundary layers has long been recognized as an impact marker. By 2007, the team had gathered enough evidence to publish their hypothesis in the Proceedings of the National Academy of Sciences. They proposed that a fragmented comet struck North America approximately 12,800 years ago, triggering the Younger Dryas cooling through multiple mechanisms. The hypothesis suggested that fragments struck the Laurentide ice sheet, causing catastrophic melting and freshwater outflow into the Atlantic. Additionally, the impact generated widespread wildfires across the continent, evidenced by the carbon-rich black mat and elevated charcoal at the boundary. These fires would have injected massive amounts of soot and dust into the atmosphere, potentially blocking sunlight and causing rapid cooling, similar to the impact winter mechanism proposed for the dinosaur extinction. The combination of atmospheric effects and ocean circulation disruption could explain the abruptness. The reaction from the scientific community was immediate and largely skeptical. Critics pointed to methodological issues, questioned whether the samples might be contaminated, suggested terrestrial explanations for the supposed impact markers, and noted the lack of a confirmed impact crater. Over subsequent years, both sides published numerous studies. Critics reported being unable to replicate some of the original findings. The original team and new collaborators responded with additional evidence, refined methods, and new sites showing similar patterns worldwide. A particularly significant development came in 2013 when researchers identified a platinum anomaly at the Younger Dryas boundary in Greenland ice cores. This discovery was important because ice cores provide exceptionally clean environmental records, minimizing concerns about contamination. Additional platinum anomalies were subsequently identified at dozens of sites across 4 continents, all dating to the same time period. This global distribution of a potential impact marker strengthened the case that something unusual had occurred at the Younger Dryas boundary. In 2018, a massive impact crater was discovered beneath the Hiawatha Glacier in northwest Greenland. Measuring approximately 31 kilometers in diameter, it ranks among the 25 largest known impact structures on Earth. Initial dating suggests it could be young enough to correlate with the Younger Dryas. While definitive dating of the Hiawatha crater remains challenging due to its location beneath ice, its discovery reignited the debate. If confirmed to be Younger Dryas age, it would represent the smoking gun that critics have long demanded as proof of the impact hypothesis. Another significant line of evidence comes from ice core records of atmospheric platinum. Research published in 2021 shows that platinum concentrations in Greenland ice spiked precisely at the Younger Dryas onset and remained elevated for about 21 years, consistent with the aftermath of a major impact. The platinum anomaly's timing aligns perfectly with other markers at the Younger Dryas boundary, including the onset of cooling. This precise chronological correlation strengthens the case for a causal relationship between a potential cosmic impact and the climate change that followed. Perhaps most compelling are the widespread discoveries of microscopic impact proxies found embedded in Younger Dryas boundary soils. These include magnetic microspherules with distinctive surface features, microscopic melt glass, carbon spherules, and nanodiamonds. Skeptics maintain that these materials could have terrestrial origins, perhaps from normal Earth processes like lightning, wildfires, or volcanic activity. But impact proponents point to their unusual composition, morphology, and most importantly, their consistent presence precisely at the Younger Dryas boundary. The debate has grown increasingly technical, focusing on minutiae of laboratory methods, the possibility of sample contamination, and competing interpretations of geochemical data. To non-specialists, these disputes can seem impenetrable, yet they revolve around a profound question. Did a cosmic impact reset the course of human history? What makes this controversy so compelling is that the stakes extend far beyond academic debate. If the impact hypothesis is correct, it would mean that cosmic catastrophe played a direct role in shaping human civilization. The development of agriculture, the emergence of complex societies, all might trace their origins to this pivotal event. More troublingly, it would suggest that similar events could happen again with little warning. While NASA and other space agencies monitor large near-Earth objects, smaller comets and asteroids, especially those approaching from the direction of the Sun, can still evade detection until they're quite close to Earth. As our investigation deepens, we must confront a paradoxical reality. The more evidence accumulates supporting the impact hypothesis, the more certain questions become increasingly urgent. If a cosmic impact triggered the Younger Dryas, what does this tell us about Earth's vulnerability? And what other established scientific narratives might need revision? Chapter 5. The Anomalies That Don't Fit. The story of the Younger Dryas becomes even more perplexing when we examine evidence that doesn't fit neatly into conventional explanations. While skeptics have focused on methodological critiques of the impact hypothesis, they've often struggled to explain several persistent anomalies that transcend the debate. Perhaps most puzzling is the extraordinary abruptness of the cooling. Ice core records from Greenland show that average temperatures dropped by approximately 10 degrees Celsius within a decade, possibly even faster. This rate of change exceeds what climate models predict for ocean circulation disruption alone. Climate scientists have long understood that the Earth's climate system contains various feedback mechanisms that can amplify initial changes. But even accounting for these feedbacks, the suddenness of the Younger Dryas onset has proven difficult to replicate in conventional climate models. This speed problem has troubled researchers for decades. In the words of paleo-climatologist Richard Alley, the Younger Dryas shift was like a light switch being flipped rather than a gradual transition. Such abruptness suggests a triggering mechanism more dramatic than ocean circulation changes. Another troubling anomaly involves the geographic extent of cooling. While the conventional meltwater hypothesis predicts cooling primarily around the North Atlantic region, evidence shows the Younger Dryas affected areas as distant as New Zealand, Antarctica, and South America. These widespread effects suggest global atmospheric changes rather than just regional ocean circulation disruption. Impact proponents argue that massive wildfires and atmospheric dust loading from a cosmic collision could explain this global signature more effectively than the conventional model. Equally perplexing is the pattern of extinctions. North American large mammals vanished with remarkable suddenness at the Younger Dryas boundary. These animals had survived numerous previous climate fluctuations over millions of years, including multiple ice ages and warming periods. Why would these species suddenly vanish during the Younger Dryas when they had proven so adaptable to past climate shifts? And why was North America so much more severely affected than other continents? The conventional explanation struggles to account for this asymmetry. Furthermore, the fossil record shows that many of these extinct animals exhibit evidence of having died suddenly, not gradually as would be expected from climate stress or even human hunting pressure. Frozen mammoths found in Siberia show evidence of flash freezing, with undigested summer plants still in their stomachs. The Younger Dryas boundary layer itself presents another anomaly. The black mat, found at numerous archaeological sites, contains unusual concentrations of materials rarely found together in nature: magnetic spherules, nanodiamonds, platinum group elements, and carbon spherules. Conventional explanations suggest these materials could have terrestrial origins, perhaps from wildfires, volcanic activity, or normal Earth processes. But their consistent presence precisely at the Younger Dryas boundary across widely separated geographic regions suggests a single, continent-spanning depositional event. The presence of nanodiamonds is particularly difficult to explain through conventional mechanisms. While some forms of nanodiamonds can be produced by wildfires or other terrestrial processes, certain types found at the boundary, including hexagonal lonsdaleite, typically require extreme pressures and temperatures. Lonsdaleite, sometimes called impact diamond, forms when graphite is subjected to the extraordinary conditions of a cosmic impact. Its presence at the Younger Dryas boundary across multiple sites suggests conditions far more extreme than normal Earth processes can typically generate. The carbon spherules found at the boundary present another puzzle. These microscopic carbon-rich spheres show evidence of having formed under high-temperature conditions. While critics suggest they might be fungal structures or products of normal wildfires, their concentration specifically at the boundary layer remains striking. Perhaps most compelling is the platinum anomaly found at the Younger Dryas boundary worldwide. Platinum group elements are relatively rare in Earth's crust, but more abundant in meteorites. Their elevated presence precisely at the boundary strongly suggests an extraterrestrial component. This platinum signature has now been found at more than 50 sites across 4 continents, all dating to the exact same time period. The consistent global distribution and precise timing of this geochemical marker is difficult to explain through any mechanism other than a cosmic event. The recent discovery of the Hiawatha crater in Greenland adds another intriguing piece to this puzzle. Though precise dating remains challenging due to its location beneath ice, initial estimates suggest it could be young enough to correlate with the Younger Dryas event. At 31 kilometers in diameter, the Hiawatha crater would represent one of the most significant impact events in the past several million years. Its location near the Greenland ice sheet aligns with the impact hypothesis suggestion that the collision triggered catastrophic ice melt and freshwater outflow. Critics correctly note that definitive dating of the crater is essential before linking it conclusively to the Younger Dryas. However, its discovery demonstrates that major impacts have occurred much more recently than previously thought, making the impact hypothesis more plausible on first principles. Another anomalous aspect of the Younger Dryas is the archaeological discontinuity it represents. The sophisticated Clovis culture, which had spread rapidly across North America, essentially vanishes from the record at the boundary. This cultural collapse is difficult to explain through gradual climate change alone. The post-Clovis archaeological record shows evidence of population decline and cultural disruption across North America. While humans certainly survived, their technological traditions and settlement patterns changed significantly. Such dramatic cultural breaks often indicate catastrophic rather than gradual change. Similarly puzzling is the appearance of new cultural adaptations immediately following the Younger Dryas onset. In the Levant, hunter-gatherers intensified their experiments with plant cultivation precisely during this period of climate stress. This counterintuitive development challenges conventional understandings. Why would humans begin the transition to agriculture during a period of climate deterioration rather than abundance? Conventional wisdom suggests agriculture emerges during favorable conditions, yet the evidence shows early cultivation intensifying exactly when conditions worsen dramatically. This paradox has led some researchers to propose that agriculture emerged not from abundance, but from necessity, a desperate response to catastrophic environmental change that disrupted traditional hunting and gathering lifeways. The Younger Dryas may have forced innovation through crisis. At Göbekli Tepe in Turkey, hunter-gatherers mobilized enormous labor resources to construct monumental architecture immediately after the Younger Dryas onset. This unprecedented project, requiring coordination of hundreds of workers, emerged from supposedly simple societies facing climate stress. The site's massive T-shaped pillars, arranged in circles and carved with sophisticated animal imagery, represent a quantum leap in cultural complexity. Their appearance immediately after the Younger Dryas suggests a response to something profound, perhaps a witnessed catastrophe that transformed worldviews. The astronomical alignments evident in the site's architecture, combined with carved symbols that some researchers interpret as depicting celestial events, raise the possibility that Göbekli Tepe commemorates the cosmic impact itself, a monument to catastrophe and survival. While critics correctly caution against overinterpretation of archaeological evidence, the temporal correlation between these cultural transformations and the Younger Dryas boundary is striking. Something profound changed in human societies precisely when this climate event began. Another troubling anomaly involves ocean sediment records. Studies of North Atlantic deep-sea cores show evidence of massive sediment pulses at the Younger Dryas boundary, deposits that appear too sudden and extensive to be explained by normal glacial processes. These chaotic sediment layers suggest catastrophic oceanic events, perhaps tsunami waves or enormous meltwater pulses, that coincide precisely with the Younger Dryas onset. Their scale exceeds what would be expected from gradual ice sheet melting or normal ocean processes. The geographic distribution of these sediment anomalies is consistent with massive waves radiating outward from impact sites in the North American ice sheet. While alternative explanations exist, the timing and scale of these deposits align remarkably well with the impact hypothesis scenario. Perhaps most difficult to explain through conventional mechanisms is the apparent simultaneous initiation of wildfires across North America at the Younger Dryas boundary. Evidence from carbon and charcoal records suggests continent-wide burning occurred with stunning synchronicity. While normal wildfires certainly occur through lightning strikes and other natural causes, their typical pattern is regional, not continental. The evidence suggests fires ignited across vast areas simultaneously, a pattern more consistent with the thermal pulse from a cosmic airburst than with normal wildfire propagation. These converging lines of anomalous evidence, the abruptness of cooling, the geographic extent of effects, the pattern of extinctions, the black mat composition, the platinum anomaly, archaeological discontinuities, and evidence for continental-scale wildfires collectively suggests something extraordinary occurred at the Younger Dryas boundary. Each anomaly might individually have conventional explanations, but their precise coincidence in time, their geographic extent, and their collective magnitude increasingly strain the conventional narrative. Sometimes, when enough anomalies accumulate, a paradigm shift becomes necessary. As Nobel Prize-winning physicist Max Planck once observed, science advances one funeral at a time. Established theories resist modification until evidence becomes overwhelming. The Younger Dryas Impact Hypothesis represents exactly this kind of challenge to scientific orthodoxy. Chapter 6. The Myths That Remember. Throughout human history, cultures worldwide have preserved stories of cosmic catastrophe. From Plato's account of Atlantis to indigenous oral traditions spanning continents, these narratives describe a time when fire fell from the sky, the world burned, and civilization collapsed into darkness and cold. For centuries, scholars dismissed these stories as mere myth, imaginative tales with no historical basis. But the Younger Dryas Impact Hypothesis raises a provocative possibility. What if these ancient stories preserve actual memories of witnessed cosmic catastrophe, transmitted through countless generations? The Ojibwe people of North America tell of a time when the star with the long, wide tail fell from the sky. It brought destruction, burning forests, boiling rivers, and darkness. Animals died, people starved. The world grew cold. This description aligns remarkably well with the aftermath of a major cosmic impact. Similar stories appear in cultures worldwide with striking consistency. The ancient Greeks spoke of Phaeton, who lost control of the sun chariot, causing worldwide conflagration. Chinese records describe a time when stars fell like rain, followed by years of cold and famine. These narratives share common elements: celestial objects falling to earth, widespread fires, subsequent darkness and cold, flooding, and mass starvation. While easily dismissed as universal human fears projected onto mythology, their consistency and specificity become more intriguing when compared to the Younger Dryas scenario. Perhaps most compelling are indigenous North American traditions that specifically mention now-extinct animals known from the fossil record. Multiple tribes preserve stories of massive, elephant-like creatures with long tusks that disappeared after a time of fire and cold from the sky. These stories often include descriptions of landscape features created by the impact, deep depressions, unusual rock formations, or areas where the soil differs from surrounding regions. Some indigenous groups maintain traditions of avoiding specific locations they associated with the catastrophe. In South America, myths describe a time when the world was consumed by fire, followed by darkness and cold. The sun disappeared, then returned different than before. These narratives often place this event at the beginning of the current age, a dividing line between ancient and modern times. Ancient religious symbolism also shows intriguing patterns potentially linked to cosmic events. Archaeoastronomers have noted that many early religious symbols, particularly spiral and concentric circle motifs, resemble the visual phenomena associated with cometary airbursts as described by modern witnesses. At Göbekli Tepe, astronomical symbolism pervades the site's architecture and carvings. One pillar appears to depict a headless human, animals, and astronomical symbols in a scene that some researchers interpret as representing cosmic impact and its devastating consequences for life on Earth. The vulture stone at Göbekli Tepe contains what some scholars interpret as a date marker corresponding precisely to 10,950 BCE, the Younger Dryas onset. Could this be a commemoration of witnessed catastrophe, carved in stone by survivors determined to preserve the memory for future generations? Skeptics correctly caution against overinterpretation of ancient symbolism. Human pattern recognition tends to find meaningful connections even where none exist. Yet the temporal correlation between these earliest monumental structures and the Younger Dryas event remains striking regardless of interpretation. Plato's account of Atlantis deserves particular attention in this context. Often dismissed as pure fiction, his detailed description includes specific elements consistent with cosmic impact, destruction in a single day and night, accompanied by earthquakes and floods and fire from the sky. Plato explicitly dates this event to 9,000 years before Solon's time, placing it remarkably close to the Younger Dryas boundary. He describes a once prosperous civilization destroyed so completely that even knowledge of writing was lost, forcing survivors to begin again like children. While Atlantis has been sought in numerous locations, some researchers suggest the story may represent a cultural memory of pre-Younger Dryas civilization, perhaps maritime cultures that occupied now-submerged continental shelves before sea levels rose following the last ice age. Rising sea levels at the end of the Pleistocene inundated vast coastal regions worldwide, areas that would have been prime locations for human settlement. Any evidence of sophisticated maritime cultures would now lie beneath 400 feet of ocean, largely inaccessible to archaeological investigation. Interestingly, many flood myths specifically mention that the catastrophe was preceded by fire from the sky, a detail that aligns with the impact hypothesis scenario of airbursts followed by melting ice sheets and sea level rise. This sequence appears in myths spanning continents. Beyond myths, physical evidence occasionally emerges that seems out of place within conventional historical frameworks. The Younger Dryas Impact Hypothesis might help explain some of these anomalies that have long puzzled archaeologists and historians. Consider the mysterious, vitrified forts found across Europe, stone structures whose rocks show evidence of having been subjected to temperatures exceeding 1,000 degrees Celsius. Conventional explanations struggle to account for the extreme heat required to melt solid stone. While traditionally attributed to deliberate firing by humans for defensive or ceremonial purposes, the temperatures required exceed what ancient wood-burning technologies could typically achieve. Could some of these structures bear witness to the thermal effects of cosmic airbursts? Similarly puzzling are ancient desert glass formations found in regions including the Libyan Desert and South Australia. These vast fields of natural glass require temperatures approaching 1,600 degrees Celsius, conditions difficult to explain through normal geological processes but consistent with cosmic impact effects. Ancient texts sometimes contain descriptions of observed celestial phenomena that align with modern understanding of cometary encounters. Chinese astronomical records from 1054 CE precisely documented the supernova that created the Crab Nebula, demonstrating the accuracy of some ancient astronomical observations. The Younger Dryas Impact Hypothesis invites reconsideration of certain archaeological anomalies as potential evidence of more sophisticated pre-catastrophe cultures. Sites like Gunung Padang in Indonesia, with potentially much earlier construction dates than conventionally accepted, warrant fresh examination. Recent discoveries continue to push back the timeline of human accomplishment. Göbekli Tepe itself forced a major revision of when humans began monumental architecture. The discovery of sophisticated cave art dating to 40,000 years ago demonstrated aesthetic capabilities far earlier than previously acknowledged. These revelations suggest our understanding of prehistoric human capabilities remains incomplete. If maritime cultures developed along now-submerged coastlines, evidence of their achievements would be largely inaccessible. The conventional archaeological record may represent only highland survivors of coastal civilizations. The consistent elements in worldwide myths, celestial objects falling, widespread fire, subsequent darkness and cold, flooding, and civilization collapse, align remarkably well with the Younger Dryas impact scenario. This correlation doesn't prove the myths preserve actual memories, but it certainly makes the possibility more plausible. If these stories do indeed preserve memories of witnessed catastrophe, they suggest the impact had immediate, devastating effects on human populations, effects dramatic enough to embed themselves in cultural memory for thousands of years. Such persistence speaks to the event's profound psychological impact. Through this lens, many religious traditions take on new significance. The widespread belief in cyclical world ages, each ended by catastrophe, might reflect cultural processing of the Younger Dryas event. The concept of divine judgment through fire from heaven could originate in witnessed cosmic trauma. Researchers like William Topping have documented indigenous knowledge preserved through centuries of oral tradition that accurately identified impact sites later confirmed by geological investigation. This demonstrates that some oral traditions can maintain accurate information over remarkably long time frames. The convergence of mythology, archaeology, and geological evidence suggests a compelling possibility. The Younger Dryas impact may represent the most recent global catastrophe to significantly reshape human civilization. Its memory echoes through our oldest stories, monuments, and cultural practices. Perhaps most intriguing is how these ancient memories might influence modern thinking. Carl Sagan suggested that widespread human fear of snakes and darkness might represent evolutionary adaptations to ancient threats. Could our fascination with apocalyptic scenarios similarly reflect cultural memory of actual catastrophe? If myths preserve memories of cosmic catastrophe, they offer a sobering lesson about Earth's vulnerability. The stories consistently portray humans as helpless before celestial forces, a humbling perspective that contrasts sharply with modern confidence in technological mastery of our environment. As we continue our investigation, we must balance scholarly caution with openness to evidence regardless of its implications. The myths may be merely stories, or they may be the oldest historical documents we possess, preserving crucial warnings from those who witnessed catastrophe firsthand. Chapter 7. The Hidden Stakes of Catastrophe. As we've explored the evidence surrounding the Younger Dryas Impact Hypothesis, a profound question emerges. Why does this scientific debate generate such intense controversy? The answer lies in the extraordinary implications that extend far beyond academic disagreement into the foundations of how we understand human civilization. If a cosmic impact triggered the Younger Dryas climate reversal, we must fundamentally reconsider humanity's relationship with catastrophe. Rather than seeing civilization as a steady progression of advancement occasionally interrupted by setbacks, we might instead view it as catastrophe-driven evolution. This perspective suggests our most significant cultural innovations, agriculture, monumental architecture, complex social organization, and religious institutions, emerged not from abundance, but from desperate adaptation to cosmic disaster. Necessity, in its most extreme form, may have mothered our greatest inventions. The implications for archaeology are revolutionary. The field has traditionally focused on gradual development models where innovations spread through cultural diffusion. A catastrophe-centric model suggests instead that simultaneous innovations might emerge across regions as responses to shared trauma. This would explain several archaeological puzzles. Why agriculture appears to emerge nearly simultaneously in multiple locations, why monumental architecture suddenly appears without clear precedent, and why complex religious symbolism emerges fully formed rather than developing gradually. For geology and planetary science, the stakes are equally high. The impact hypothesis suggests that significant cosmic collisions occur much more frequently than previously estimated. Rather than being extraordinarily rare events, civilization-threatening impacts might occur on timescales relevant to human history. This frequency assessment directly influences contemporary priorities regarding planetary defense. If major impacts occur every few thousand years rather than millions, the urgency of developing detection and deflection capabilities increases dramatically. The Younger Dryas debate has direct relevance for current policy. For climate science, the implications are particularly significant. If the Younger Dryas cooling was triggered or amplified by impact-related atmospheric dust loading, it demonstrates climate vulnerability pathways not currently incorporated into most climate models. Our understanding of climate stability may be incomplete. More troubling is the evidence for how rapidly climate can shift. The Younger Dryas cooling happened within decades, possibly even faster in some regions. This abruptness challenges assumptions about how much time we might have to adapt to climate tipping points once they're crossed. For human psychology and culture, the implications extend even deeper. If our ancestors witnessed and survived a cosmic catastrophe, the collective trauma may have shaped fundamental aspects of human thought, from religious concepts to risk assessment to intergenerational knowledge transmission. Our oldest religious motifs, divine judgment through fire from heaven, world ages ended by catastrophe, celestial deities demanding appeasement, take on new significance when viewed as potential cultural processing of witnessed cosmic trauma rather than merely abstract theological concepts. Similarly, the peculiar human capacity for apocalyptic thinking, our tendency to imagine end-of-world scenarios, might represent an adaptive psychological mechanism developed in response to actually having experienced near extinction. We may be wired to anticipate catastrophe because our ancestors survived one. Perhaps most profound are the implications for how we understand civilization itself. The conventional narrative portrays agriculture and settlement as natural progressions, inevitable developments once human cognitive capacity reached a certain threshold. The catastrophe model suggests otherwise. In this alternative view, humans were perfectly successful as hunter-gatherers for hundreds of thousands of years. Agriculture, with its increased labor demands and reduced dietary diversity, represented not progress but desperate adaptation to catastrophically altered environments where traditional lifeways no longer functioned. The timing aligns remarkably well with this interpretation. Early evidence of plant cultivation appears before the Younger Dryas, but full commitment to agricultural lifestyles emerges primarily afterward, particularly in regions most affected by the climate reversal. Necessity, not preference, may have driven this transition. This perspective challenges our fundamental assumptions about progress. What we call civilization, with its social hierarchies, specialized labor, monumental architecture, and intensive resource exploitation, might represent emergency adaptation rather than advancement. Our modern world may be built on catastrophe. For indigenous cultures whose oral histories have preserved catastrophe accounts for millennia, validation of the impact hypothesis would represent long overdue recognition of traditional knowledge. Their stories, long dismissed as superstition by Western science, might contain accurate historical information. This scientific validation would have profound implications for how we value traditional knowledge systems alongside conventional scientific approaches. Indigenous perspectives on catastrophe, resilience, and adaptation might offer crucial insights for navigating contemporary environmental challenges. For those working in planetary defense, the stakes are immediate and practical. NASA and other space agencies currently focus primarily on detecting objects large enough to cause extinction-level events. But the Younger Dryas scenario suggests smaller impactors can cause civilization-level disruption. A fragmented comet or asteroid in the half-kilometer range, much smaller than dinosaur killer-class impactors, but still devastatingly powerful, could arrive with minimal warning, particularly if approaching from the direction of the Sun. Our detection capabilities for such objects remain limited. The recent unexpected airburst over Chelyabinsk, Russia in 2013, where a 20-meter meteor exploded with the force of 30 Hiroshima bombs without prior detection, demonstrates these limitations. Imagine a similar object 100 times larger or multiple fragments arriving simultaneously. Contemporary civilization, with its complex supply chains, just-in-time manufacturing, and interdependent systems, may be more vulnerable to such disruption than our prehistoric ancestors. We have optimized for efficiency rather than resilience, potentially increasing our catastrophe vulnerability. Climate scientists increasingly recognize that the Earth system contains tipping points, thresholds beyond which gradual changes trigger rapid, nonlinear responses. The Younger Dryas represents a natural experiment in crossing such thresholds, offering crucial insights for our current climate predicament. If the impact hypothesis is correct, it demonstrates how external forcing can trigger these nonlinear responses, producing climate effects far exceeding the direct energy input of the initial trigger. This amplification through feedback mechanisms has troubling implications for current anthropogenic climate forcing. For geologists, The debate highlights how much remains unknown about Earth's recent past. The discovery of the Hiawatha crater demonstrates that major impact events have occurred much more recently than previously recognized. What other significant events might be missing from our geological understanding? The controversy also illuminates the sociology of science itself, how established paradigms resist change, how interdisciplinary evidence can fall between specialized fields, and how extraordinary claims face extraordinary scrutiny. This process, while sometimes contentious, ultimately strengthens scientific understanding. But the greatest stakes may be philosophical. The impact hypothesis suggests that random cosmic events have shaped human destiny more profoundly than we've recognized. Our entire civilizational trajectory, from hunter-gatherer bands to agricultural villages to industrial society, may have been catastrophe-directed. This perspective challenges both religious narratives of divine purpose and secular narratives of inevitable progress. Instead, it suggests cosmic contingency, that humanity's path has been shaped by random celestial events whose timing and location determined which adaptations would emerge. If true, this has profound implications for how we view our future. Rather than assuming steady progression or predetermined development, we might instead recognize that catastrophes, whether cosmic, climatic, or self-inflicted, represent the primary drivers of major cultural transformation. This recognition doesn't mean abandoning hope or agency. Rather, it suggests focusing on resilience, adaptability, and preservation of knowledge through potential bottlenecks. Our ancestors apparently survived cosmic catastrophe. Their example might guide our preparations for future challenges. The debate over what triggered the Younger Dryas has expanded from a narrow scientific controversy to a profound questioning of human origins. Were we shaped primarily by gradual adaptation and cultural diffusion? Or did cosmic catastrophe repeatedly reset our developmental trajectory, forcing radical innovation? The answer matters not just for understanding our past, but for navigating our future. If catastrophe has repeatedly shaped human destiny, we would be wise to incorporate this understanding into our preparations for challenges ahead, from climate change to pandemic disease to technological disruption. As new evidence continues to emerge, from additional Younger Dryas boundary sites, from improved dating of the Hiawatha crater, from ancient DNA studies of population bottlenecks, from archaeological discoveries pushing back technological timelines, the picture grows increasingly complex. What remains certain is that approximately 12,800 years ago, something extraordinary happened. The Earth plunged suddenly into cold. Ecosystems collapsed. Animals vanished. Human cultures transformed. Whether triggered by cosmic impact or internal Earth processes, this event reshaped our world. And as we'll explore next, the implications extend even further than we've considered thus far. Because if the Younger Dryas was indeed triggered by cosmic impact, it represents just one episode in what may be a recurring pattern of celestial catastrophe, a cycle that may not have ended. The evidence increasingly suggests that the Younger Dryas impact was not an isolated event, but part of a cycle of increased cometary activity. Multiple researchers have identified evidence for similar events both earlier and later in the Holocene, a pattern potentially linked to solar system dynamics. If correct, this pattern would fundamentally alter our understanding of Earth's climate stability and human vulnerability. The relatively stable climate of the past 10,000 years, the foundation upon which civilization developed, may represent not the norm but a fortunate interlude between cosmic catastrophes. As we prepare to examine this evidence, we must confront a troubling possibility that the security we've assumed throughout recorded history may be more precarious than we've recognized. The next installment of cosmic disruption may already be approaching, with implications we've barely begun to comprehend. Chapter 8: The Battle of Explanations. As we've explored the evidence supporting the Younger Dryas Impact Hypothesis, we must now examine the strongest competing explanations. Scientific progress requires considering all viable theories, and several alternative mechanisms have been proposed to explain the Younger Dryas cooling without invoking cosmic impact. The most established alternative remains the meltwater pulse theory. According to this model, as the massive Laurentide ice sheet retreated northward, enormous volumes of freshwater collected in glacial Lake Agassiz along its southern margin, a lake larger than all the modern Great Lakes combined. When ice dams containing this freshwater failed, the theory suggests that massive outflow poured into the North Atlantic, disrupting the ocean circulation pattern that brings warm tropical water northward, the Atlantic meridional overturning circulation. This shutdown caused rapid cooling across the northern hemisphere. This explanation has dominated scientific understanding of the Younger Dryas for decades. It connects known glacial features with documented ocean circulation mechanisms. Computer models confirm that sufficient freshwater input could indeed disrupt ocean circulation patterns, triggering regional cooling. Recent research has strengthened aspects of this theory. Geological evidence confirms that glacial Lake Agassiz drained rapidly around the Younger Dryas onset. Sediment cores from the Gulf of Mexico show evidence of increased freshwater outflow through the Mississippi River system during this period. Furthermore, isotope studies of ocean sediments confirm changes in water circulation patterns coinciding with the Younger Dryas. These changes align with what would be expected from a major freshwater pulse disrupting the Gulf Stream and related ocean currents. However, several problems persist with the meltwater pulse theory alone. First, geological evidence suggests the primary meltwater drainage route may have been through the St. Lawrence Seaway rather than directly into the Arctic Ocean as initially proposed, a pathway less likely to disrupt ocean circulation. Second, the timing remains problematic. Some studies indicate the major meltwater pulses occurred either too early or too late to trigger the Younger Dryas cooling. This chronological mismatch challenges the direct causal relationship central to the theory. Third, the meltwater theory struggles to explain the abruptness of the cooling as recorded in Greenland ice cores. Ocean circulation changes typically produce temperature shifts over centuries rather than the decades or less indicated by some high-resolution climate records. Finally, the geographic extent of cooling, reaching areas distant from the North Atlantic, exceeds what would be expected from ocean circulation disruption alone. Additional mechanisms seem necessary to explain the global signature of the Younger Dryas event. A second competing theory involves changes in atmospheric circulation patterns triggered by shifting ice sheet configurations. As the Laurentide ice sheet retreated, its diminishing height and extent would have altered wind patterns across the northern hemisphere. These atmospheric reorganizations could have redirected storm tracks, changed precipitation patterns, and altered heat distribution across continents. Such changes might explain some regional aspects of the Younger Dryas cooling without requiring either ocean circulation disruption or cosmic impact. Computer climate models support this possibility, showing that ice sheet configuration changes can indeed produce significant climate effects. The atmospheric circulation theory has gained support from researchers seeking mechanisms beyond ocean circulation to explain the Younger Dryas patterns. This theory's strength lies in its ability to explain regional variations in the cooling pattern, why some areas experienced more severe effects than others. It also potentially explains changes in precipitation patterns evident in paleoclimate records that ocean circulation disruption alone cannot account for. However, the atmospheric circulation theory also faces challenges. Like the meltwater hypothesis, it struggles to explain the extreme abruptness of the cooling. Atmospheric patterns typically shift gradually as ice sheets change, not suddenly as the Younger Dryas records indicate. Additionally, this mechanism alone cannot easily explain certain geochemical signatures at the Younger Dryas boundary, the platinum anomalies, nanodiamonds, and microspherules found across continents. These require separate explanations if not attributed to cosmic impact. A third alternative involves solar forcing, changes in the sun's output affecting Earth's climate. Some researchers have proposed that solar activity declines significantly at the Younger Dryas onset, reducing energy input to Earth and triggering cooling through direct radiative forcing. Evidence for this comes from beryllium-tin isotope records in ice cores, which can serve as proxies for past solar activity. Some studies show changes in these isotope ratios coinciding with the Younger Dryas, potentially indicating reduced solar output during this period. The solar forcing theory connects with established understanding of how solar variability affects climate. The Little Ice Age of the 14th to 19th centuries has been partially attributed to the Maunder minimum, a period of reduced sunspot activity and lower solar output. However, solar forcing faces perhaps the most significant challenges of the alternative theories. Most critically, The magnitude of solar variability appears insufficient to produce cooling as severe and rapid as the Younger Dryas without additional amplifying mechanisms. Furthermore, solar forcing alone cannot explain the geochemical anomalies at the Younger Dryas boundary. It offers no mechanism for producing nanodiamonds, microspherules, or platinum enrichment. These would require separate explanations if the solar theory were correct. What emerges from examining these competing theories is that none fully explains the entire constellation of evidence surrounding the Younger Dryas event. Each accounts for some aspects while struggling with others, particularly the abruptness, geographical extent, and boundary layer geochemistry. This realization has led some researchers to propose hybrid models. Perhaps a cosmic impact triggered rapid ice sheet melting, causing both atmospheric dust loading and freshwater pulses into the ocean. Such a scenario would combine mechanisms, potentially explaining more evidence than any single theory. Critics of the impact hypothesis often focus on specific methodological issues rather than addressing the full body of evidence. They may challenge particular laboratory techniques used to identify nanodiamonds or suggest contamination explains platinum anomalies, without offering comprehensive alternative explanations. This pattern, critiquing specific elements rather than providing alternative frameworks that explain all the evidence, characterizes much of the opposition to the impact hypothesis. It's a methodologically sound approach to scientific scrutiny, but it leaves explanatory gaps. The scientific method demands that theories be falsifiable, capable of being proven wrong through evidence. The Younger Dryas Impact Hypothesis meets this criterion. Specific predictions made by the hypothesis can be tested against new evidence as research continues. For example, the impact hypothesis predicts that samples from the Hiawatha crater in Greenland should date to approximately 12,800 years ago. As dating techniques improve and more samples become available, this prediction will be either supported or refuted. Similarly, the hypothesis predicts that Younger Dryas boundary materials should contain elevated levels of impact-related proxies compared to layers above and below. Blind testing of samples by independent laboratories can verify or challenge these predictions. What makes the Younger Dryas debate so compelling is that it transcends disciplinary boundaries. It involves geology, archaeology, paleontology, climatology, astronomy, and physics. This interdisciplinary nature complicates evaluation, but also enriches the investigation. Each discipline brings different methodological approaches, evidentiary standards, and theoretical frameworks. Geologists may focus on stratigraphic integrity, archaeologists on cultural discontinuities, climatologists on cooling mechanisms, and physicists on the thermodynamic requirements for nanodiamond formation. These different perspectives sometimes talk past each other rather than engaging directly. The result can appear more contentious than the evidence itself would suggest if evaluated comprehensively. Specialists may miss patterns visible only when viewing the entire body of evidence. As we consider these competing explanations, we must acknowledge that science progresses through exactly this kind of contention. Established theories should face rigorous challenges. New hypotheses should bear the burden of extraordinary evidence for extraordinary claims. What emerges from this scientific battleground is not necessarily a single victor, but a more refined understanding that may incorporate elements from multiple theories. The truth about the Younger Dryas may be more complex than any current explanation fully captures. Perhaps most importantly, the competition between these theories drives new research, new methodologies, and new discoveries. Whether or not the impact hypothesis ultimately prevails, it has already enriched our understanding of Earth's recent past and humanity's relationship with cosmic forces. The debate continues because significant evidence supports elements of each theory, yet none completely explains all observations. This scientific tension, uncomfortable but productive, pushes research forward toward more comprehensive understanding of one of Earth's most significant climate events. Chapter 9: The New Science of Cosmic Vulnerability. Recent scientific advances have transformed our understanding of cosmic impacts, challenging long-held assumptions about their frequency and effects. The traditional view held that major impacts occurred rarely, perhaps once every million years, and that evidence would be obvious in the form of large, preserved craters. New research reveals a more complex reality. Impacts on the scale capable of triggering significant climate effects may occur much more frequently, perhaps on timescales of thousands rather than millions of years. And their evidence can be subtle, especially for impacts on ice sheets or oceans. The Chelyabinsk meteor that exploded over Russia in 2013 delivered a sobering lesson in cosmic vulnerability. Despite modern detection capabilities, this 20-meter object arrived entirely without warning. The airburst released energy equivalent to 30 Hiroshima bombs, injuring over 1,500 people. If scaled up to the size range suggested for the Younger Dryas Impactor, perhaps 1 to 2 kilometers in diameter, such an object could cause regional or global catastrophe. More troublingly, our detection capabilities for comets remain limited, especially for those approaching from the direction of the Sun. Researchers examining ice cores and marine sediments have identified evidence suggesting cosmic impacts may be clustered rather than randomly distributed through time. These clusters might occur when Earth's orbit intersects debris streams associated with disintegrating comets. The Taurid meteor stream, for instance, contains debris from Comet Encke and potentially larger fragments. Astronomical studies suggest this stream's density varies over time due to gravitational interactions with Jupiter and other planets. Earth periodically encounters denser portions of the stream. Some researchers, including astronomer William Napier, propose that the Younger Dryas impact may have been part of such an encounter with the Taurid complex. This model suggests multiple fragments striking Earth over a relatively short period rather than a single large impactor. This multiple impact scenario might explain the wide geographic distribution of impact markers at the Younger Dryas boundary. Rather than a single crater, we would expect scattered smaller impact sites, airbursts, and widespread effects, precisely what the evidence seems to indicate. Perhaps most intriguingly, several studies have identified potential impact markers at other time horizons throughout the Holocene, not just at the Younger Dryas boundary. These include layers dated to approximately 10,900, 9,600, 7,000, 5,000, 4,200, and 2,800 years ago. These dates correlate with periods of abrupt climate change, cultural disruption, and in some cases, societal collapse as documented in the archaeological record. The 4,200-year-old event, for example, coincides with the collapse of multiple civilizations, including the Old Kingdom in Egypt. This pattern suggests a troubling possibility that cosmic impacts have shaped human history more frequently and profoundly than previously recognized. Rather than being extraordinary events outside human timescales, they may represent recurring drivers of historical change. New analytical techniques have strengthened the case for the Younger Dryas impact. Improved methods for identifying nanodiamonds, more sensitive platinum detection, and advanced microscopy have confirmed earlier findings while addressing methodological critiques from skeptics. A study published in Scientific Reports in 2019 identified a platinum anomaly in the Greenland ice sheet precisely at the Younger Dryas boundary. This discovery is particularly significant because ice cores provide exceptionally clean environmental records, minimizing concerns about contamination. The platinum spike persists for approximately 21 years in the ice core record, consistent with the time required for platinum-rich dust to settle from the atmosphere following a major impact. This precise chronology provides compelling support for a cosmic trigger for the Younger Dryas. In South America, recent studies have identified Younger Dryas boundary markers at multiple sites, including platinum anomalies, magnetic microspherules, and evidence of widespread burning. These findings extend the geographic footprint of the event well beyond North America. Similarly, research in Europe, Asia, and Africa has identified impact proxies at the Younger Dryas boundary. The global distribution of these markers strengthens the case for a cosmic event rather than a regional phenomenon limited to North America, as initially proposed. The recent discovery of the Hiawatha crater in Greenland represents perhaps the most significant development. First identified in 2018 through radar mapping beneath the ice sheet, this 31-kilometer impact structure ranks among the 25 largest known impact craters on Earth. Initial dating suggests the Hiawatha crater could be as young as the Younger Dryas, though precise age determination remains challenging due to its location beneath ice. If confirmed to be 12,800 years old, it would represent the smoking gun that critics have demanded. Even without definitive dating, the Hiawatha discovery demonstrates that large impacts have occurred much more recently than previously thought. This revelation alone forces reconsideration of Earth's cosmic vulnerability, regardless of whether this particular crater relates to the Younger Dryas. New paleogenetic studies of human populations reveal intriguing patterns consistent with the impact scenario. Analysis of ancient DNA shows evidence of population bottlenecks and rapid expansions around the Younger Dryas timeframe, suggesting demographic disruption followed by recovery. Archaeological evidence increasingly supports rapid cultural change following the Younger Dryas onset. Recent excavations at Göbekli Tepe have strengthened its dating to immediately after the Younger Dryas boundary, confirming that monumental architecture emerged precisely during this period of climate stress. The site's intricate carvings continue to yield new insights. Astronomical interpretations of certain symbols suggest possible recording of celestial events. The labor mobilization required for construction, estimated at hundreds of workers, represents unprecedented social organization for hunter-gatherers. This archaeological evidence presents a fascinating paradox. The most significant early advances in human cultural complexity occurred not during periods of abundance and stability, but immediately following catastrophic disruption. Necessity, rather than surplus, may have driven innovation. Genomic studies of animal populations add another dimension to the picture. Analysis of ancient DNA from North American mammals shows evidence of population crashes precisely at the Younger Dryas boundary, independent confirmation of the timing of ecological disruption. Perhaps most compelling are new chronological studies using synchronous events as markers. Recent research used the distinctive geochemical signature of the Lacher Sea volcanic eruption, which occurred shortly before the Younger Dryas, to precisely align climate records across continents. This improved chronology confirms that cooling occurred simultaneously across widely separated regions, a pattern difficult to explain through ocean circulation changes alone, which should produce time-transgressive effects spreading gradually from the North Atlantic region. The evidence increasingly suggests that multiple mechanisms may have operated simultaneously. A cosmic impact could have triggered atmospheric changes, ice sheet destabilization, meltwater pulses, and ocean circulation disruption, creating a perfect storm of climate-forcing factors. This integrated model helps explain why the competing theories each capture some aspects of the evidence while missing others. The Younger Dryas may represent a complex cascade of effects triggered by an initial cosmic impact rather than a single-cause event. The most significant recent developments come from the field of complex systems theory. Climate scientists now recognize that Earth's climate system contains tipping points, thresholds beyond which small changes can trigger rapid, nonlinear responses through feedback mechanisms. The Younger Dryas may represent a natural experiment in crossing such thresholds. Whether initially triggered by cosmic impact, meltwater pulses, or some combination of factors, the climate system appears to have switched rapidly between stable states rather than responding gradually. This perspective reconciles the debate to some extent. The impact hypothesis may identify the initial trigger, while the ocean circulation theory correctly identifies the mechanism through which this trigger was amplified into global effects. Both contain elements of truth within a complex systems framework. As we integrate these scientific advances, a new understanding emerges, one that acknowledges both the evidence for cosmic impact and the complex Earth systems through which its effects were propagated. This integrated perspective may ultimately transcend the either/or debate that has characterized the controversy. The scientific journey continues. New analytical techniques, additional field sites, improved dating methods, and interdisciplinary collaboration promise further insights. The Younger Dryas represents not a settled case, but an active frontier of scientific discovery about Earth's recent past and cosmic vulnerability. Chapter 10. The Truth Behind the Controversy. After examining the evidence, counterarguments, and recent scientific developments, we can now address our central question. What does the evidence truly show about the Younger Dryas event? The answer emerges not as simple vindication of either side, but as something more nuanced and ultimately more profound. The weight of evidence now strongly supports a cosmic component in the Younger Dryas onset. Multiple independent markers, platinum anomalies, nanodiamonds, microspherules, and high-temperature melt products, appear precisely at the Younger Dryas boundary across widely separated geographic regions. These markers show distinctive characteristics consistent with cosmic impact rather than terrestrial processes. The platinum carries an extraterrestrial isotope signature. The nanodiamonds include hexagonal forms requiring extreme pressure. The microspherules show features indicating rapid cooling from high-temperature melts. Most importantly, these markers appear synchronously across continents precisely at the Younger Dryas boundary, a pattern extremely difficult to explain through multiple local processes coincidentally occurring simultaneously worldwide. Such synchronicity strongly suggests a global triggering event. The recent identification of a platinum spike in Greenland ice cores precisely at the Younger Dryas boundary provides particularly compelling evidence. Ice cores offer exceptionally clean environmental records, minimizing concerns about contamination that have been raised regarding soil samples. The discovery of the Hiawatha crater in Greenland, potentially young enough to correlate with the Younger Dryas, adds another significant piece to the puzzle. While definitive dating remains pending, its mere existence demonstrates that substantial impacts have occurred in the geologically recent past. However, the evidence does not support the most extreme versions of the impact hypothesis. There was likely no dinosaur killer scale impact 12,800 years ago. Instead, the evidence points toward either a single modest-sized impactor, perhaps 1 to 2 kilometers in diameter, or multiple smaller fragments. The most probable scenario involves an encounter with fragments from a disintegrating comet, perhaps associated with the Taurid complex. Such an encounter would produce airbursts, ground impacts, and widespread environmental effects without necessarily creating a single large crater. This cosmic encounter appears to have triggered a complex cascade of Earth system responses, including atmospheric dust loading, widespread wildfires, ice sheet destabilization, meltwater pulses, and ocean circulation disruption. The initial impact was amplified through multiple feedback mechanisms. In this integrated perspective, elements of competing theories are reconciled. The impact hypothesis correctly identifies the initial trigger, while the meltwater and ocean circulation theories correctly describe amplification mechanisms that transformed a cosmic encounter into global climate change. This resolution helps explain why the scientific debate has been so contentious. Different researchers, examining different pieces of evidence, could legitimately reach different conclusions. The full picture emerges only when integrating evidence across multiple disciplines and timescales. The truth behind the controversy reveals something profound about how science progresses. Major advances often occur at disciplinary boundaries where evidence from different fields converges. The Younger Dryas debate demonstrates both the challenges and the power of truly interdisciplinary science. For human history, the implications are revolutionary. The transition from hunter-gatherer lifeways to agriculture and settled communities, the foundation of everything we call civilization, appears to have been catalyzed by cosmic catastrophe rather than gradual cultural evolution alone. This doesn't mean that humans were simply passive victims of celestial forces. Rather, it suggests that our ancestors demonstrated extraordinary resilience and adaptive capacity in the face of catastrophic environmental change. Their innovations in response to crisis shaped all subsequent human history. The earliest monumental architecture, complex social organization, and sophisticated religious symbolism emerged precisely during the aftermath of the Younger Dryas. Not during periods of stability and abundance as conventional theories might predict, but in response to witnessed catastrophe. This pattern suggests a profound revision of how we understand cultural evolution. Innovation may be driven more by necessity than surplus, more by crisis than stability. The foundations of civilization may represent adaptations to cosmic catastrophe rather than the fruits of gradual progress. For modern humans facing accelerating climate change, this historical insight carries significant implications. It suggests both vulnerability and resilience, that human societies can face existential threats from climate shifts, but also that innovation and adaptation can emerge from crisis. The evidence further suggests that Earth's cosmic neighborhood may be more hazardous than previously recognized. Rather than impacts being extraordinarily rare events, they may occur on timescales relevant to human civilization. Our cosmic vulnerability may be greater than we've assumed. Yet the evidence also reveals the extraordinary interconnectedness of Earth systems. Impact effects were amplified through complex feedbacks involving atmosphere, oceans, ice sheets, and ecosystems. Understanding these interconnections is crucial for addressing contemporary environmental challenges. Perhaps most importantly, the Younger Dryas case demonstrates how established scientific narratives can require significant revision when new evidence emerges. Science advances not through defending orthodoxy, but through remaining open to evidence that challenges existing paradigms. The debate continues and should continue. Science thrives on constructive controversy, rigorous methodological critique, and competing interpretations. New evidence will emerge, techniques will improve, and our understanding will deepen. The final chapter has not been written. What we can now say with confidence is that approximately 12,800 years ago, Earth experienced an extraordinary event that transformed climate, ecosystems, and human societies. The evidence increasingly points to a cosmic trigger that initiated a complex cascade of Earth system responses. This conclusion doesn't represent the triumph of one hypothesis over others, but rather the emergence of a more integrated understanding that transcends the either/or framing of the initial debate. The truth emerges not as vindication of extremes, but as synthesis of multiple perspectives. For those who have followed the Younger Dryas controversy, this resolution may seem anticlimactic. Science rarely delivers absolute certainty or simple narratives. Instead, it offers increasingly refined approximations of complex realities, always subject to revision when new evidence emerges. Yet within this nuanced conclusion lies something profound, a glimpse of how cosmic forces and Earth systems interact to create the environmental stage upon which human history unfolds. Our ancestors witnessed and survived cosmic catastrophe, and their response shaped our world. As we face our own environmental challenges, this perspective offers both caution and hope. Caution that Earth systems can change more rapidly than we might prefer to believe. Hope that human innovation and adaptation can emerge from even the most severe disruptions. The Younger Dryas event stands as testimony to both Earth's vulnerability and humanity's resilience. In understanding this ancient catastrophe, we gain insight not just into our past, but into our relationship with a cosmos that is both more threatening and more directly connected to our lives than we often recognize. As our journey through the Younger Dryas mystery concludes, we return to where we began, standing at the boundary between what we know and what remains hidden. The evidence reveals not just an ancient climate event, but a profound truth about humanity's relationship with cosmic forces. Our civilization exists within a complex dance of celestial mechanics. The Earth orbits not through empty space, but through cosmic neighborhoods occasionally cluttered with debris, fragments of comets, stray asteroids, dust streams that intersect our path at regular intervals dictated by orbital mechanics. These intersections are not random, but cyclical. The same gravitational forces that shepherd planets around the Sun create patterns of recurrence, temporal rhythms that bring Earth repeatedly into contact with cosmic debris streams. What happened 12,800 years ago could happen again. Indeed, some researchers suggest we remain within the same cometary debris field that delivered the Younger Dryas impact. The Taurid meteor stream, associated with Comet Encke, contains not just dust, but larger fragments that occasionally pass uncomfortably close to Earth's orbit. This perspective transforms how we understand human history, not as an isolated planetary story, but as intimately connected to cosmic cycles. Our ancestors encoded this knowledge in myths, monuments, and oral traditions that we are only now beginning to decipher with scientific tools. Perhaps most humbling is the recognition that our technological civilization, for all its apparent dominance, remains vulnerable to the same cosmic forces that transformed our ancestors' world. Our complex systems, global supply chains, interconnected economies, digital networks, may be more fragile, not less. Yet alongside this vulnerability stands the evidence of human resilience and adaptability. Our ancestors not merely survived cosmic catastrophe, but created innovative responses that formed the foundation of civilization itself. From crisis emerged transformation rather than extinction. As we face contemporary challenges, climate change, biodiversity loss, pandemic disease. This deep historical perspective offers both sobering caution and grounds for hope. Earth's systems can change with shocking rapidity, yet human creativity thrives precisely when confronted with existential challenges. The Younger Dryas story reminds us that we inhabit not just a planet, but a cosmos, one where events beyond our atmosphere can transform life on Earth. In acknowledging this cosmic dimension of our existence, we recover a perspective our ancestors understood, but modern humans often forget. The cycle continues. Earth orbits. Debris streams await. Will we recognize the patterns our ancestors encoded in their earliest monuments and myths? Will we develop the technological foresight to detect and deflect cosmic threats? The answers may determine our future as much as they reveal our past.